section.
Slide number? Last two are always the slowest.
Oh, I definitely not. I'm right. That's right. I definitely, the times that I'm here in my drive time is literally all the. It's not fun.
I'm gonna look at it, find his name right away. Right after you said it.
Okay, a couple things before we get going. Tony had mentioned that now all of the concrete testing is actually right at the truck, not at the point of placement. So the slides I had shown that make sure you discharge some from the pump, actually it doesn't even really control anymore. So we'll keep that in mind. And then Linda, you have a question about the monetary deduction. It actually is in the spec. Page 385. Okay. So for the rest of you, $500 penalty for every 5-minute period. But there is also something I think in the special revision to maybe strengthen. Okay, so our next presentation is about concrete, and there is some duplication, and we've purposely left some duplication in there just because bridge decks are important. And so we have Jacob Dave, who is the structural concrete engineer for the MnDOT, and about 4 to 5 years of experience. We're trying to remember. But we also, he had a little bit of time with WSP, some time with Semstone, so a great expert. So with that, we'll try to wrap up in an hour and a half. Okay. Okay.
Yeah, thanks, Paul. Hi, like Paul said, I'm Jacob Gabe. I'm the assistant concrete engineer in the concrete community. I've been with MnDOT about 4 or 5 years, can't really remember, but I've been dealing with concrete my entire career, so it's kind of something that I've found a way to nerd out on. We're going to talk structural concrete, but before we get into that, I did
Paul's gonna say, I don't think that went around. So.
Okay,
You got it, run past it.
on that website, you can check out things like certified ready-mix plants. So plants that they need to get certified every year in order to deliver concrete to state work. So you can see plants that are part of that certified ready-mix program. You can also look up approved mix designs. So like our general RMX mix designs, you can see if an RMX sheet number is approved or rescinded on a website. So if you're using like a 3B52 or 3S52A or something like that, and that's what gets submitted to you, you can check the RMX number on the website to see that it's been reviewed and it's in the system. You can also look up approved aggregates that are going to be used in our concrete mixes. I'm not quite sure why you would want to do that, but the information is there. It's not just the approved aggregates, but it's also the properties that the ready-mix producer is going to use when they design their concrete mixes, and then other forms and worksheets that you might need when it comes to concrete on your projects. So it's a really good resource. If you've got a question, I'd go there first, and then you can always call one of us at the concrete office when we try to get you. So let's talk about high performance bridge deck mixes. These are performance-based specs, which is new since about 10 years, where we switched over to contractors actually designing mixes. There is trial batching that's required, usually done in a lab like an AMT or a WSP or Terracon or Brown or something like that. Before, when those mixes get submitted for review, we look at the trial batch results to see if they meet the requirements that are specified before they can be used on projects. And that's for our 3Y HPC mixes, SCC mixes that you might run into, mass concrete. I also have up there, it's a 3Y LCHPC. You don't see that in the spec book or the special provisions, but it is, a special provision that we have on the shelf for situations where we might not have access to fly ash or other SCMs, but you won't run into that. probably, but I'm gonna put it up there just for awareness. So, talking a little bit more about three-way HPC, there's things, so there's fibers in that, we were talking about that earlier, so we've got fibers in all three-way HPC mixes. There are versions that could use lightweight sand for internal curing or lightweight coarse aggregate to actually make the concrete lighter than conventional concrete. And we've got a slide on that coming up. And then we've got our self-consolidating concrete and then mass concrete, which you would run into on like abutments or piers where you're using the 3D52 or like the footings that are large. So when you look at the spec for the three-way HPC, this is the mixed design table that's in 2401. Then this is essentially what the ready mix producer is looking at. This is really the only recipe that we kind of give them. So when we say it's performance based, we're telling them, hey, these are the only parameters that your mix design needs to be in. On top of the lab testing that's required for things like shrinkage, rapid chloride permeability, strength, freeze-thaw durability, and scaling. And so they'll use this to develop their mix design, submit it to my office. I review them, make sure that they're adhering to the spec and the requirements, and then sign the mix as reviewed by MnDOT. Now, recently, and maybe you run into this, but we used to say we approved the mix design, but the lawyers got involved and told us we can't say approved anymore. So when I send the mix back, I would say, you know, this mix has been reviewed or whatever like that. So when you see a signed mix, that means it's been reviewed by the concrete office. Doesn't necessarily mean it's approved. Apparently there's some legal strategy behind it, but anyway, just so you would know that. So what goes in, when we're talking about concrete, obviously we use cement. Cement makes up our paste. And, you know, historically we were using type 1s and type 1-2 cements, but about 3-4 years ago in this state, all of the suppliers, save for one up in the Duluth area that brings in cement from Turkey, all the suppliers are only giving ready-mix producers type 1L cement. And all type 1L is it's type 1 with about 10% fine limestone ground mixed into it. And we don't really see any property changes in the concrete using type 1L cement. Some contractors might say that finishing is a little bit different, so the water demand's a little bit different, but it's not enough to really change materially what happens out on floors using type 1L cement. And that's in response to kind of the global target that the cement industry has on their back with their global warming potential. So in order to make the cement, it releases a lot of CO2. So if they can take 10% of that out of every mix and put in this limestone, which is essentially inert from their carbon release that they have, they're basically gaining 10% on their global warming potential right there. And so it's not just MnDOT that is kind of pushing for that kind of stuff. It's, in general, the cement industry across the globe is looking for ways that they can cut down on the carbon and push it out. So all that is to say, basically every concrete mix that we pour in Minnesota has type 1L cement. Then we also have our SCMs. One of the main ones we use in Minnesota is fly ash. So this is a byproduct of coal combustion power plants. It's classified in two classes, Class C or Class F. The thing I like to think about when I talk about the difference between Class C and F is Class C has some cementitious properties to it, so it will react in the presence of water and start forming calcium silicate hydrate, where Class F does not. Class F needs the byproduct from an initial hydration reaction in order to continue making the calcium silicate hydrate. We're generally looking at 10 to 30% replacement when we're using fly ash. In the MnDOT spec, up to 15% can be replaced on our RMX mixes without moving to a level 2 mix design submittal, which would include a little bit additional testing and some strength results. But producers can replace up to 15% without doing that additional testing. We see higher replacements in our HPC mixes, simply because we're trying to pass some of those tests like our rapid chloride permeability test, or we're using reactive sands that might need some ASR mitigation. And so those are all the things that I'm looking at when I get a mix design submitted, hey, are we meeting all these requirements? In Minnesota, we're actually pretty fortunate compared to other regions across the country in that we have not only one, but two pretty good sources, or actually really good sources of fly ash that we'll probably have for the foreseeable future. There's other places in the country where you can't get fly ash at all, and that's simply because we're taking coal power plants offline. Now there is, a lot of ash that, before we had figured out that it's really good in concrete, that would get landfilled, and so there's a lot of really smart people working on can we use that, can we use that going forward into, as we're moving away from burning coal for power. But in Minnesota, we do have a couple pretty good sources of fly ash, so we're pretty fortunate in that regard, because fly ash actually is really good for making strong, durable concrete. Other SEMs are slag, like slag. Slag is a byproduct of steel production. If you ever hear anyone say ground granulated blast furnace slag, that's what it used to be called, but that's a mouthful, so we just shortened it down to slag cement. Dosage rates are a little bit higher when you're using slag, we, in Minnesota, we typically see slag in mass mixes. And so when we're trying to keep the heat of hydration low, we'll see higher replacements of slag because it can work to do that. So we generally don't see it in HPC mixes or like curb and gutter mixes or things like that. But when we are trying to keep the heat of hydration low, we'll use slag cement. And then there's also silica fume, sometimes referred to as microsilica. This is a byproduct of the silicon metal or the alloys production. It's low dosages compared to like fly ash or slag where you're using up to 5%. But the thing about silica fume is it's much smaller than cement or fly ash or slag when you're looking at just the actual grain size. And so because of that, it has a higher surface area when you're using it, which means a higher water demand. And so silica fume mixes have a higher propensity for things like plastic shrinkage, cracking, or crazing. MnDOT uses silica fume in some overlays, some bridge deck overlay mixes, especially D7. They use silica fume overlays more than other districts do. And so if you get on a project that is using silica fume, one of the things that's really important to talk about is when you're at the pre-activity meeting is that evaporation rate, the chart that we were just looking at previously. And I've got a couple slides more on that. But the reason why is because silica fume is really sensitive to the moisture conditions that you're placing it in. If you place it, if you get it down in place without, and you're adhering to some of those moisture condition requirements that you need to be aware of, silica fume mixes are really, really good in terms of the strength and the permeability that we get out of them. So that's one of the reasons why they're used. So this is just a quick chart to kind of show, from a plastic properties to a hardened properties, what happens in the plastic stage of the concrete when you use these different SEMs. But then also the hardened properties, at the bottom part of the chart kind of tells you, why do we throw all this stuff into concrete? Well, it's because it basically improves all of the different properties that we're looking for. From strength to permeability to ASR mitigation and sulfate attack. I mean, they just make our concrete much more durable and long-lasting. So, like we mentioned, in the high-performance concrete bridge deck mixes, we're using fibers in all of them now. So, one of the things that prior to using fibers in bridge decks, we had a max slump of 4 inches. But when we started putting fibers in there, we saw a need to increase that to 5. So on a HPC mix, your slump range is 2 to 5 inches. And these are used for random crack control. They're not structural. They're just there for drying shrinkage cracking that happens. They don't prevent cracking, but what they do is when a crack forms, they stitch it together and stop it from propagating and also from opening up. So if you think about a crack happens and you've got fibers in the mix, that's basically going to stitch it together. Works the same way that like rebar would do when we have our secondary reinforcement. All we're doing is trying to hold cracks tight together, and that's how fibers do it too. Now, the thing about the fibers that we use for MnDOT is they're a combination of macro and microfibers. In general, when you're talking about synthetic fibers, you've got macrofibers and microfibers. Microfibers are used for plastic shrinkage crack mitigation, but once the concrete hardens, those macrofibers at the low dosages that we're using them for don't really do anything. They're just kind of there, not bad, not good. But the macrofibers, they don't really do anything during the plastic part of when the concrete is setting. It's when it's hardened, that's when the macrofibers come into play to stitch cracks together. And so we use a combination of those for fibers that need to be on, in order to be on the APL. Just so you know that. And there are methods for incorporating the fibers. And so the first method that's in the spec is you can open the bag and distribute the fibers on the aggregate belt. Rarely done, but it is allowable. By far, what most producers do is the second option, which like the chicken feed option, where you open up the bag of fibers and you hand feed it into the back of the truck. One of the reasons why is all the fiber manufacturers will say that their packaging is water soluble, and you might think it is, but we tended to see a little bit more balling when we were just throwing fibers in the sacks, and letting that packaging dissolve. So we don't allow any of the water-soluble packaging to be in the concrete mix, and a lot of the actual ready-mix producers have policies that have the same effect anyway. So those are the two methods. I do know that fiber manufacturers are trying to develop a mechanical way to introduce fibers into the mix, but I haven't seen one that works yet. So if you are on a project and you've got someone saying, hey, we got this blower that we're going to try and use with the fibers, why don't you let the concrete office know too, so we might want to see how one of those works. But for now, those are the two ways that you can incorporate fibers into concrete mix. Let's talk about lightweight aggregates real quick. So there's two forms of lightweight aggregate. You've got your coarse aggregate and you've got your fine aggregate, your sands. With coarse aggregate, you're literally just trying to make the concrete lighter. So you go from about 150 pounds per cubic foot to about 105 to 150. And with lightweight fine aggregates, we use that for internal curing. Now both of these, before they're incorporated into the concrete mix, need to be submerged for a couple weeks because these are very porous materials here. You can actually see the little holes on the aggregates themselves from the coarse aggregate. That all needs to be filled with water before it's incorporated into a mix, concrete mix. Otherwise, it's going to draw the mixed water out. And so that's why we need those to be saturated before they are incorporated into the mix. Now with internal curing, MnDOT has tried this on a few decks in the last 5 or 6 years, and it didn't go super great in terms of a production standpoint. So we don't really use those a lot for internal curing, but we have tried it before, and it might be something that maybe we'll circle back on. But I just wanted to include it on here so you guys were aware of lightweight aggregates that could potentially be used on projects. So this is what a mixed design submittal form will look like that gets submitted to the concrete office. And so, obviously they'll include the SP number, they include the agency contact is, what plant they're coming out of. When you get a project-specific mixed design, it is also plant-specific now too because of the way AASHTO works, where we're entering the mixed designs in. So there's some ready-mix producers that like to submit a backup mix as well. And prior to using AASHTO, they all just submitted it on one mix design and said we're going to come out of these plants. but because ASHTO ware is JMF specific now, it also means it's plant specific. So you might have one bridge deck with, you know, at least 2 mix designs submitted. Generally, the second one is only there for the backup in case something happens to that plant or whatever. But then, so one other thing I'm looking at is what are the materials that they're using, and I'm checking to see, okay, are they on the APL? Do they have the correct properties of the aggregates that they're using? And then does their mix design meet that table that I showed you previously? And I'm going to look at this and compare it to the lab testing that they submit with the mix design as well, to make sure that the mix that was tested in the lab matches the mix that they're submitting. You know, obviously we want to make sure that we've got a representative result from our lab testing, and so, you know, down to the pound on these materials that they're using, making sure it's the exact same mix design that was tested in the lab. So once the review is done, you'll see it signed by someone in the concrete office, either myself, this one's signed by Maria, the concrete engineer. Send it back to the ready mix producer and the agency contacts saying, hey, this mix has been reviewed by the concrete office, it's good to go to use on the project. When the truck shows up, it's going to have a certificate of compliance with it, and that certificate of compliance will list off all the materials that were included in that particular load of concrete. And so, you know, it's probably good practice to, you know, every once in a while take a look at that certificate of compliance and make sure it matches the mix design that was reviewed for the project. You know, so like for instance, the fly ash that's used is the Prairie States here. So we've got the MnDOT abbreviation for Prairie State Class F, PSGMAL. Make sure that that matches what was on the reviewed mix design. Sometimes, you know, a silo gets switched or something, it doesn't get changed in the batch computer, but it's important that the mix that's actually delivered is what was reviewed and signed by the concrete office, and that's all included on the certificate of compliance. Some key points in the special provisions, the trial bridge deck placement for high performance concrete, so a minimum of 14 calendar days prior to the actual placement. We want to do a trial of using the same mix that they're going to use for the deck production. We want at least 2 10-yard loads for that. And really all that is we want to make sure that we can produce the concrete, get it to the site, have it in spec, and so we're not, you know, trying to figure stuff out the day of the deck pour and getting, you know, fiddling with the first 2 loads of the concrete, which you're probably going to do anyway. I don't know if any of you have been on the deck pours where the tension's a little bit higher when that first load or 2 shows up to make sure that everything's in spec, and then, you know, once the wheels get greased, everything goes off. So when I was working for a producer, I actually really liked having the trial placement because it allowed us to kind of make the tweaks to the mix, so we weren't doing it the day of the deck pour. But we can waive this, so the contractor should request and submit the necessary documentation in order to waive this. And then what that means, they need at least 3 successful placements in the last 5 years using the same exact mix design. So I've seen it before where I get like, hey, am I okay to waive this placement? And I'll see the history, and it's 3 different mix designs. They're all technically 3-way HPC mixes, but they're different mix constituents, different materials being used. It should be the same exact mix design from the same plant, similar haul time, similar time of year, in order to waive that. So if you have any questions, if you ever get that request, feel free to contact me and I can definitely give you a recommendation on it. But we can waive it in case it's something that's been done and there's a lot of history with that mix design. For bridge slabs, at least 14 calendar days prior to the placement, we're going to provide a slab placement and curing plan for each bridge to the engineer for approval. And so that's going to include things like the anticipated concrete delivery rates, when are we going to start to finish, what type of material, labor, or equipment do we need in order to do the placement effectively, how many work bridges are we going to use, how many people are going to be responsible for the various tasks in order to accomplish the pour, and then any bulkheading methods and materials that you propose to use if the contractor can't maintain that proper placement rate, or let's just say like a random storm comes up and it starts pouring, and you're not going to pour concrete in the rain anymore. How can we bulkhead? Then 2 to 4 calendar days before placement, we're going to review the information in detail provided in the placement hearing plan at a pre-placement or pre-activity meeting. And people who should be at that meeting are like the contractor and their superintendent foreman, the engineer, the concrete supplier, and probably the pump supplier too, if they're going to be on the job. And then prior to the actual day of the deck placement, 3 hours before the anticipated time of beginning the bridge deck placement, we're going to provide, the contractor is going to provide a National Weather Service forecast to the engineer. It has to be from the National Weather Service. It can't be like from WeatherBug or AccuWeather or something like that, because they're all just a little bit different. And so in order to have like an even playing field, this is where we're taking the forecast from. It's from the National Weather Service. And in that, we want to make sure that there's not any forecasted rain 2 hours prior to, during, or up to 2 hours after the placement. We also want a less than 30% chance of precipitation for the entire placement window in that placement plan. And then we're also looking at the combination of air temperature, relative humidity, concrete temperature, and wind velocity that produces an evaporation rate of less than 0.2 pounds per square foot per hour. And so that's that nomograph that Paul was showing earlier. One thing to point out though is that I have seen in some of the silica fume overlays that actually, this is not 0.2, it's actually 0.1 or 0.15. So if you're ever on a silica fume overlay project, just double check what the evaporation rate requirement is. But yeah, so this nomograph is in your is in the spec book, and this is how we would determine what our evaporation rate is 3 hours prior to. I'm also developing an Excel spreadsheet that we can use, which would make this a little bit easier. But the basis is this nomograph here, and so all you would take is you've got your air temperature at 77 degrees. You go up to your relative humidity, and you can look on your forecast from the National Weather Service, and it'll give you a relative humidity for the area you're in. Once you get to that curve, once you intersect with that curve, you go to the right, and that will be your concrete temps. And so, up to 3 hours before, you don't have your thermometer in the concrete at that point, but the ready mix producer probably has a pretty good idea on what their concrete temps are running, so you can use that to determine this number here. So once you intersect with that line, you go down to your wind speed. So whatever your forecast says your wind speed is at that time, when you intersect with that, you go to the left, and that's where you come up with your evaporation rate. So in this example, it looks like we're a little bit above 0.2. So in this case, we either want to stop the pour until conditions are better, or we're going to do some things to maybe help out that evaporation rate. We could do things like wind blocks. So, it's a windy day, but you put a wind block up where that wind can't really affect the concrete surface. Well, then you're going to reduce your evaporation rate just by changing the wind speed that's included in there, or fogging. So like on our silica fume overlays, it's actually required to have equipment on site to be able to fog the slab. And so what you're doing there is you're putting a really fine mist over the top of the concrete. It's not so much that it's falling out and puddling on the surface, but really what you're trying to do is increase the relative humidity just over the surface of the concrete. So it's not, you don't have dry air pulling mixed water out of the concrete. That's the whole idea of it. Or you could even switch to night pours too. And a lot of times in the urban areas, particularly in Twin Cities, we're doing night pours anyway, and that's more of a contractor decision, partly because of traffic and truck availability. But when you get out of state, it's a little more difficult to do night pours, but it's always an option. But these are things that can happen if we don't get here, or we're not aware of our evaporation rate, where that that surface might start drying up and we can't finish it, we can't close it up. We might start getting plastic shrinkage cracking or crazing or dust and things like that. That's why we want to be aware of conditions that will place the concrete. Some other key points, a straight edge. So we don't want to use a bowl float. We're using a straight edge, and the only reason we're doing this is we're trying to knock down any high areas. We don't want to put any more energy into the surface than we need to. Just think about the more energy you put into the surface, the more chance of surface defects. And so when you float concrete, what you're doing with this, this tool on the side here is you're pushing down coarse aggregates and seeding them into the surface, which is a good thing, but also your big well pan is helping with that. But then you're also pulling cream up, right? So the more cream you pull up, the weaker that pace is going to be. So we don't want to put more energy into that surface than we need to. And so we use that straight edge just to knock down any high areas, and that's it. We're not trying to close the concrete, put a really nice hard finish like you would in like a warehouse store or something like that. Also, finishing aids. So things like finishes, what's the other one? Like con film. We don't allow those. They work, but the thing is they're about 1 part chemical and 9 parts water. So they're mostly water. And really the way that they work is if you put them on, you spray it onto the concrete, it's almost like a sacrificial layer of water that's going to evaporate away before the moisture of the mixed water can evaporate away. And really, how these are used in the field by a lot of people is they put them on, they hear the brand name finishes, I'm going to put it on and I'm just going to start finishing the concrete. Well, really what they're doing is they're just increasing the water cement ratio right at the surface by working that water in. And so there's a specific time that's really hard to monitor unless you know exactly what you're looking for and you've done it a lot on when you can get onto a concrete that has been treated with finishing. So with that in mind, we just don't allow it. Same goes for blessing of the slab. Now you might see this where take the paintbrush, dip it in the water, and you flick it out onto the concrete and you get a little more cream. It seems like, oh, this is great. I can close this surface up. I've got a lot more cream to work with here, but again, what you're doing is increasing the water cement ratio of just at the surface. And so, as we know, the higher the water cement ratio is, the lower the durability will be. So you will more than likely have surface issues at places that you place the concrete on. In cases where the contractor just got caught, this shouldn't be this or using con film or finishes or something like that. It shouldn't be the routine operating procedure, but there are times where something came up, something happened, or the mix isn't quite right, where it's really hard to close up. Go ahead and get it closed up, but then have a conversation with the contractor about how are we going to avoid this in the future, because we don't want this happening. And so, if it comes up, you can do what you need to do to get the concrete poured, but this shouldn't be a regular occurrence. It shouldn't be part of the normal operating procedure. For form removal, we're going to maintain a concrete surface temperature of 40 degrees or greater during the curing period any time of the year. If the concrete surface temperature drops below 40 during that curing period, we're going to notify the engineer and make adjustments to the curing to increase the surface temperature above 40 as prescribed in the curing plan. If the concrete surface temperature drops below 40 during the curing period, add an additional day to the minimum curing period for each day the temperature drops below 40, and then provide additional protection as required in accordance with 2401 3G5 protection against cold weather. We do have an APL for form release agents, so take a peek at that and make sure that what they're using out on the project is on the APL. And really the main thing we're looking at is the environmental evaluation of these products. So that's how you get on the APL for form release agents. So I think this might be a redundant question, but we'll do a quick pop quiz here. If we're looking at table, I can't even read here, 2401.3-2. What is the required strength to open traffic next to a barrier going off of this table? Yeah, you guys already all did it, right? So normally, okay, we need to be 45%, but we've got that note, and we gotta look at the footnotes here. So if it's a traffic barrier, we're gonna go on here, we need at least 4,000. So you guys okay? Now, why do we have the spec that we have for minimum period of keeping forms on or not? Well, this was a research project that was done, I don't know how many years ago, but it basically showed, okay, what happens to the concrete at different ages if the forms are removed early or late or whatever. So the way that the spec is written is to kind of find that happy medium, right? Of we get the service life that we're looking for out of the concrete while also not, impinging on the progress of the project. So if we pull the forms too early, we're going to lose a lot of service life. Is essentially what this table is doing. And that's where this was like the basis of writing up the table and the spec on minimum period for cold cure. So we do have the acceptable curing methods, a membrane curing method, the curing blanket method, wet curing method, and then the form curing method, which we just talked about. So with our curing methods, depending on the element that you're pouring, they'll have different curing methods that are acceptable or not. And that's all listed out in table 2401.3-3. The curing plan needs to be submitted to the engineer for acceptance at least 14 calendar days prior to any concrete placement. And if there's any failure to adhere to that plan, it will result in form curing for the next 3 placements. And so a lot of times we want to recycle those forms as quickly as we can, or if we want to use them elsewhere on the project. And so if we're not adhering to the plan correctly, then those forms need to stay on, which is not ideal from a contractor perspective, but neither is not curing the concrete properly. Also, a big thing when it comes to curing is protection against rain. So we want to protect the concrete from damage due to rain or snow. And so near the site, we want to have materials that can protect the edges and surface of the concrete if it's going to rain or if it does rain. Should any damage result, the engineer will suspend operation until corrective action is taken. And that damaged concrete may be subject to 1503 or 1512. And we also aren't going to start concrete placement when it's raining or snowing. That might seem obvious, but we had a project this year where it was downpouring, they were pouring concrete, and so we got them the order with the concrete office and said, hey, they're pouring and it's raining, it's raining out. And we're like, wait, what? What are you doing? So we had to write it into the spec. It wasn't in there, like, do not place concrete if it's raining. It's in there now as a special provision, but we shouldn't be placing concrete when it's raining. Because what can happen, especially like a bridge deck, if you think about this, so if it's raining, you're going to wash away the surface. Especially at like these upper drain areas here, you can really see that coarse aggregate there. You wash away all the paste from the surface. And you can also run into some issues, whether being able to finish it right, get your texture on it right. The durability of the concrete is going to be in question, and it's a costly repair. Coming out to diamond grind is not cheap, and so we want to, it's generally something that the contractor probably pays for if they're pouring in the rain, but there's also schedule implications to it. There's going to be probably months of negotiation on who pays for what and when they're going to get out there, so we might as well just try and avoid it and protect it from getting rained. Here's one where I'm not quite sure how this happened, but placing the concrete, and obviously it looks really wet. Sorry, freak storm happened or something and it started raining. So this is that concrete during placement, and then 1 year later we've got these cracks that are forming from that rain damage. So we want to try and avoid that. Now, membrane curing. We're going to apply a curing compound homogeneously, provide uniform solid white opaque coverage on all exposed concrete surfaces. So that, quick rule of thumb, we've got an application rate of 150 square foot a gallon. That's kind of difficult to monitor and track out in the field when you're spraying the membrane cure on. And so a good rule of thumb, easy to remember, is if you're putting a white sheet of typing paper or copy paper down onto the cured surface and it kind of blends in, then you've got enough coverage. So you don't need to be saying, hey, you're at 149 square foot per gallon, Mr. Contractor, you need to move it up. Well, if you can put a white sheet of paper down, then you're good. We do have specs for this and an APL for curing compounds. They need to be the alpha-methylstyrene AMS curing compound. That's the one you generally see. Linseed cure is also available, but most of the time we're using the AMS cures. Like I said, we have an APL for the curing compounds, and we're not going to accept a cure that's not on this approved products list. Here's some examples of some membrane curing compounds, some good, some not so good. We'll start at the top left here. It looks like if you were to put a white sheet of typing paper down here, that it would blend right in. So I would say these two guys are doing a pretty good job of getting the coverage down here. In the middle, I'm not quite sure what happened here. I think, obviously the nozzle was gummed up or something. It wasn't spraying a fan out like it would normally. That's obviously not very good coverage if you can see bare concrete underneath it. So I think maybe Ron Mulvaney had this picture taken just so we could put it into these types of slides as an example, but that's obviously not very good coverage. Top right here, everything looks like it's going pretty well on this concrete pool, but I would venture a guess that it's been more than 30 minutes since this concrete was placed and they're back over here. And so this is the situation we're trying to avoid with that 30-minute timeline. We don't want that concrete that is otherwise not being worked to just be exposed to the elements here, and we're just losing mixed water out of it. So there's a good chance that you're going to have some surface defects from that surface drying out prematurely. But the bottom left here, this looks pretty good too. I would say, some of these darker areas, maybe we got to hit a little bit more with the curing compound, but it looks like pretty good coverage. But then in the bottom right here, maybe our plan wasn't so good because we don't know how to get to the middle of the slab. It looks like we just walked around with the wand to try and get as far out as we could. And they do have a bridge here, probably for texturing, but one more would have been great so that we can get to the middle here. Because this might as well not cure at all because the whole middle isn't getting covered up. So remember, equal to a white sheet of typing paper, adhere to the curing plan, look at those curing plans when they get submitted. With our curing blanket, after finishing without marring the surface, we're going to cover with pre-wetted burlap or curing blankets. We're going to envelop all exposed concrete to prevent the loss of water vapor. We're going to cover with a 6 mil white plastic sheeting over a layer of wet burlap or wet curing blanket and overlap that a minimum of 12 inches. And do not allow the burlap or curing blankets to dry out during the curing period. This is what that might look like. Pretty similar to how we're going to cure bridge decks, which I'll get to in a couple of slides here. With the wet curing method, cover the surface with pre-wetted burlap as soon as no marring would occur and overlap that burlap a minimum of 12 inches. We want to pre-soak that burlap for a minimum of 12 hours prior to placement. And we're not going to put dry burlap sprayed down after it's applied on the surface. Because what Paul mentioned earlier, that dry burlap is just going to suck mixed water out of the concrete. And then we want to keep it continuously wet for the minimum curing period. You can use things like soaker hoses or sprinklers. And we're not going to allow sheets or streams of water that could erode the fresh concrete. So we want some water to keep the burlap wet, but not so much that we're draining a bunch of water off the deck there. If the forecast calls for ambient temperatures to fall below 32 degrees, we're going to suspend conventional wet curing and switch to another acceptable curing method. Obviously, if it's 32 degrees or less, water is going to freeze. We don't want freezing water on our concrete that we're trying to cure. The form curing method, when the forms are left in direct contact with the concrete, other curing methods are not required except for exposed surfaces and for cold weather protection. Use another acceptable curing method if forms are removed prior to the completion of the minimum curing period. So you got the minimum form cure period and then the minimum curing period. A lot of times the form cure is less than the curing period, so if they have enough strength, they can move the forms off, but we still want to have some curing period left. That might be where they come in and you know, wrap poly around like a abutment or something, a stem or something that's coming out. So, bridge deck concrete curing. We're going to use conventional wet curing consisting of pre-wetted burlap covered with 6 mil white plastic sheeting in accordance with the following. We want to place the burlap to cover 100% of the deck area without visible openings. We're going to place the wet curing within 30 minutes after final strike off of the concrete surface, and we're going to keep the slab continuously wet for an initial curing period of at least 7 calendar days. And we're going to use a work bridge following the finishing machine in order to put that burlap down. And apparently this is a pretty famous floor, and Paul used it as well. But the one thing to point out on this is this contractor was a little bit over and above. They put this lath down and nailed it down to the forms so that that plastic sheeting wasn't going to blow up, which you sometimes see happens. This is a really good example of a contractor paying attention to details, making sure that you know, this plastic's going to stay in place during the curing period. So deck curing and protection, depending on the final surface of the bridge deck, whether you're, you know, it's a monolithic deck with the final finish when you place it, or if you're doing a low slump overlay, it's a structural slab, that will dictate the curing method that's acceptable or allowable. And that's all in table 24013-4. Again, we want to apply the curing method within 30 minutes of final strike off. And when wiring of the broom finish or tying surface finish to the bridge deck slab is a concern, the engineer may allow curing compound prior to putting the burlap down. I think this is taken advantage of a little bit though. Every time I go out to like it seems a lot of times when I go out to like a rural bridge deck placement that we're spraying it down with AMS rather than using the pre-wetted burlap. And yeah, I've heard various reasons why, but I think, you know, this should again, like, you know, blessing the slab, we should try to use that the wet curing method as much as possible, and only in certain situations where just there's no other choice, then we can use that AMS. Now the difference is they both work well for curing, but the difference between a wet cure and curing compound is that the curing compound, if it's placed properly, will trap all of the mixed water into the surface and cure the concrete. The advantage that the wet cure gives is that you provide a moisture source for the concrete if it needs it. So it might seem counterintuitive where we don't want to work water into the surface. Well, that's us doing something to the concrete, where if we put wet curing down, that concrete, you know, hey, there's a moisture source here that I could use, it's going to pull the moisture out itself. So you're not doing anything extra to it. And so you see in studies that, you know, the concrete that's wet cured is just slightly better in terms of like strength and durability than concrete that has membrane curing compound. Now that's not to say that membrane is bad, it's just why wet curing is preferred if it's possible. Now here's an example of the wet curing method. So you've got your screed, the screed placed in the concrete, the final strike off, and then you've got your work bridges on the back that they're placing the wet burlap down. Now for low slump overlay, the curing requirements for those, we're putting that membrane curing compound down within 30 minutes if you're doing a low slump overlay. And as soon as the concrete can be walked on without damage, we're going to place the wet burlap on top of that curing compound. And we're going to maintain that burlap in a wet condition for those 4 days of that curing period. We switch to cold weather concrete. So ACI 306 defines cold weather as a period when more than 3 successive days the average daily air temperature drops below 40 degrees and stays below 50 for more than 1/2 of any 24-hour period. Darn it, I knew I needed to add an E in there, I just couldn't find it when I was going through this slide. I remember that. But in our spec, the spec defines cold weather as October 1st to April 15th when we're north of the 46th parallel, and October 15th to April 15th when you're south of the 46th parallel. And that's, you know, you might have conditions where it's still warm out, right? It's not necessarily cold weather if it's early October. But I think this is good from everyone's on the same page on who's defining what as cold weather. We don't see this in other parts of the MnDOT spec, but it is in the concrete bridge construction that you've got dates like this that define what actually is considered cold weather. So for cold weather concrete and for our protection plan, we're not going to place concrete until the engineer provides written acceptance of a cold weather protection plan. We want to embed sensors for all bridge slabs. We want 2 of them in case one fails. We've got a backup one. We want to preheat any forms, in-place concrete, reinforcement bars, or the top of flanges on beams to a minimum of 40 degrees because we don't want cold materials pulling heat out of our mix that wants heat in order to hydrate. We're going to provide insulated forms insulation or heating and housing facilities to maintain a concrete surface temp between 60 and 120 degrees during that curing period. And then we're going to gradually discontinue that cold weather protection. So about 20 degrees during any 12-hour period, 20-degree change, until the surface temperature equalizes with the ambient air temperature. If we just pulled our cold weather protection and it was 60 degrees, nice and toasty, and it's 10 degrees or 0 degrees outside, if we just pulled that protection, we can shock the concrete and you can get some thermal cracking that happens from it. So we need to gradually reduce that so we can avoid any of that thermal cracking that can happen. If you're looking at like bridge slabs, box girder bottom slab, and box girder webs, we want, with air temperatures below 36 degrees, we're going to house and heat. And if there's temperatures above 36 but falling below 34 during the curing, you can house and heat after the pour. I think this is from the 35W bridge when they were casting the box girder segments. They just had a house and heat situation in here. Now, the one thing to think about if you are in this and you're using a combustion source of heat, we want this to be exhausted outside of the housed area. If we're exhausting the combustion source inside the housed area, you can lead to rapid carbonation of the surface, which ends up with like a dusty, chalky feeling on the surface. That's from that carbon dioxide reacting with the concrete. So it needs to be exhausted outside of the housed area if you're using combustion source for heat. For a bridge deck dry out period, so if the traffic is open before April 15th on a bridge deck that was placed in cold weather concrete, we're going to remove the conventional wet cure at the end of the curing period, and then for the next 25 calendar days or until April 15th, we're going to house and heat to prevent the temperature from falling below 40 degrees. This will allow the concrete to dry out after we've cured it. We want that water to leave, so before we expose it to cold conditions, we don't have, we have the least amount of water in the concrete as possible to avoid any freeze-thaw damage. For low slump overlays, we're not going to place when temperatures are below 40 degrees unless we house and heat. There's not any placements before April 15th, after September 15th north of the 46th parallel, or after October 1st south of the 46th parallel. And for a cold weather protection plan, we want to keep the concrete above 60 degrees for the first 4 calendar days and not expose the concrete to temperatures lower than 40 until at least 26 calendar days after the initial 4-day cure period. Now, curing does not equal prepared for full loading. So think about things like pier caps with cantilever for setting beams. Just because the cure period is done doesn't mean we can set beams. We still need to break some control cylinders to figure out our strength of concrete that it can accept beam setting on it. Or like backfilling wing walls, casted plates, culverts for backfilling your construction traffic, things like that. We need to know the strength. The cure period doesn't tell us what the strength of the concrete is. So don't equate that with prepared for loading. Now some keys to keep in mind for cold weather concrete. We want to, there's obviously heat and use appropriate cure methods. We're going to heat or warm our concrete materials so that the concrete shows up 50 to 90 degrees, whether it's middle of summer, middle of winter, that concrete, fresh properties needs to be within 50 to 90 degrees while it's being placed. If we're using hot water, we don't want that water to be above 180 degrees at the plant because then we could risk flash set of our concrete. Our aggregates, if the producer is heating the aggregates, we don't want those to be above 130 degrees because then we could risk some bond problems, the paste in the aggregate. using insulated forms of blankets to take advantage of that hydration reaction, keep that heat in just like we wear a coat outside. Using space heaters or surface heaters. Again, make sure that those are exhausted out of the area that we're using it if you have house and heat for there. And then we also want to monitor that strength development because that's what gives us our freeze thaw, the stronger the concrete is. The 20-degree rule, set time and strength gains will double or halve for every 20-degree change. So 50 degrees will take twice as long as 70 degrees to set. And then the 500 PSI rule, so concrete can withstand a single freeze event when it's reached 500 PSI. After that, we're looking for basically full strength in order to resist freeze thaw cycling and ice results that don't necessarily cause surface issues, but I'll get into that in a few slides coming up here. Concrete delivery and placement, we're going to allow concrete to be delivered up to 90 minutes. There's special testing for delivery times greater than 90 minutes. So if you're in a rural area, your plant's pretty far away, you don't think you can get the concrete to the site and discharge within 90 minutes, we can accommodate that. There's just some special testing that might be needed for that if you're in that situation. We want all admixtures added at the plant with minor adjustments in the field. Typically, our water reducers being adjusted in the field or air and training. We don't want any water added after 60 minutes. We do allow one admixture dosing adjustment with 2 gallons of water. It is allowed after 60 minutes, but that's just one admixture dosing adjustment. No additional water allowed after 1 cubic yard has been discharged. This gives the contractor time to take a look at the concrete and see if they want to make any changes to that mix. We also allow the use of retarders on basically every bridge deck we're going to do. It's going to start out with retarders in it because we want to load those beams up prior to the concrete setting so we don't have any cracking issues. And so basically all the retarders do is they put like a candy coating on the cement. That candy coating will wear away and then the cement hydration will take off. Actually, a quick aside on retarders, when Master Builders, formerly BASF, initially introduced theirs called, I forget what it's called, but anyway, their retarder, they're based out of Cleveland. They batched a load in Cleveland and drove it to Las Vegas for the World Concrete Show to demonstrate that they can put a concrete to sleep using their retarders for that full time of driving it to Vegas, and then they placed it like a slab or something like that. I always thought that was kind of funny to prove out that, hey, our stuff works. Approvals needed if we're using superplasticizers and accelerators. Particularly accelerators, we generally only see those in cold weather concrete, and there needs to be special conditions in place if we're going to use our type Cs and needs for accelerating admixtures. On-site fuel adjustments for bench slab concrete, only admixtures that were originally incorporated into the mix are allowed with the exception of DMAs. We're going to mix 1 gallon of water addition per cubic yard of concrete, including any water necessary to dilute admixtures. This may be added on site provided the additional water is available to add per the certificate of compliance. And anytime we make any adjustments to the concrete mix, we want to mix that load for a minimum of 5 minutes or 50 revolutions after any additions. And then we also need to do any tests after any of the required acceptance testing after the adjustments are made. Now for air content, anytime you have a type 3 mix, concrete mix for MnDOT type 3, that's air and trained concrete. That means our target air content should be 6.5% with a range of 5 to 8.5. And so if you are taking an air test and you pull like, you get like a 5.1, it's technically you can accept that concrete, but you should probably let the contractor or the ready-mix producer know that they need to increase the air content to get as close to that 6.5% as possible. Now with that 3YL CHPC mix that I mentioned earlier in the presentation here, that has a different air content target of 8%. But again, you're probably not going to run into this. I'm just including it here for awareness. It's not acceptable to knowingly place failing material into the work. The testing range should be 1 test per 100 cubic yards, including the first test. And then we're still testing the first load every day. Now, if we talk about concrete pumping, and particularly with air content testing, Used to be, prior to last year, we had point of placement acceptance testing. So that means if you're pumping a bridge deck, you gotta go get the concrete at the end of the pump, take it to wherever your testing site is to perform a testing there, and then probably do a correlation throughout the day so you can figure out what the difference is, the air before going into the pump and what the air is after the pump. And so then you wouldn't need to constantly be going out to take your samples at the end of the pump. You could just apply a correlation factor. But that also changes as the pump configuration changes too, so that wasn't always a tried and true method. But subsequent to that, there was quite a bit of research done by a professor at Oklahoma State University that proved that pumped concrete, what happens to that pump, or that concrete inside the pump, particularly all the high pressures that are in the pump, is that air actually dissolves. And so when you are pumping concrete, you know, there's always a saying in the concrete world that air is either going to go up, down, or stay the same when you pump. Generally what you see is that the air, you knock air out of it when you pump it. Well, that's that dissolved air that doesn't show up in your air content testing right after it's been pumped. But what happens is that air comes back after you stop working the concrete. And so with that research, the results of that research, that's why we changed it to point of delivery testing rather than point of placement testing. So you can take your acceptance testing prior to pumping. That's what we're taking the acceptance tests now. And if you don't believe that testing, just take a glass, fill it up with water, and put it on your nightstand tonight. When you get up in the morning, you'll see you've got air bubbles that are climbing up the sides of that, because that water also has some air in it. It's been through pumps and everything that have dissolved that air out. It's the same idea behind too of like cracking a can or something like too. You've got lots of a can of soda or something like that. You've got lots of pressure inside that can. You release it, and that's where all the bubbles get released. Same idea that happens here with pumped concrete. Talk about vibration. We're going to place the concrete as close as possible to its final location. We don't want to be using the vibrators to move the concrete around or use them as a shovel. And then we want that vibrator to go directly and vertically into the concrete and remove. And we're going to utilize a pattern, again, not using it as a shovel. So we want the vibrator to go in and out. We don't want to be dragging it around and drag concrete around with it. But if we don't consolidate well enough, or we have under vibration, you pull the forms here, that's a bad day, right? You pull the form, then you're kind of surprised what happened here. So now we're talking about how do we repair this and salvage this. So it's really important that we're making sure that we're consolidating concrete properly. Now, vibration monitoring. So we placed our concrete, we're done with the placement, and now it's gaining strength. We're in the cure period, we're gaining strength. We also want to protect it from vibration. We've got heavy equipment and other things happening on construction sites that can influence the concrete when it's gaining strength, and so we want to monitor the vibrations that are imparting onto that concrete. So after the first 5 hours after the placement, we don't want to disturb the concrete until it reaches 2,000 psi minimum. There's two methods. The primary method is looking at what our compressive strengths of our concrete are, and then what type of equipment is working near that concrete. So depending on what type of equipment it is and what strength we're getting out of that concrete, that's how close that equipment can be to that concrete. There's also another method where you can use a sensor to measure the peak partial velocity. So again, based on the strength of the concrete in question, the peak partial velocity changes. So the stronger the concrete is, the more vibration that the concrete can withstand. Is essentially what it comes down to. So for concrete sampling, using ASTM C172 sampling requirements that went into effect in June of 2020, the minimum sample size is 1 cubic foot, so that's about 145, 150 pounds of concrete. We recommend wheelbarrows for concrete field testers. You got a wheelbarrow to gather your sample. It's really a whole lot better than a couple. I've done 5-gallon pails too. And that's a lot more work than using a wheelbarrow. Concrete strength in the 2016 spec book, MnDOT switched to minimum 28-day calendar compressive strength. MnDOT's noticing that strength gain is taking longer for some through HPC bridge deck mixes. We recommend making one set of 356-day cylinders in addition to the 28-day set. If you look at the current schedule of materials control, HPC, Mass, and SEC, we all asked for a set of 56-day cylinders as well. Deficient strengths may be subject to monetary adjustments, and low cylinder strengths, which are greater than 500 PSI below the design strength, then investigation is required, and coring may be required. Also for cylinders, just some reminders, we want to take care when fabricating and curing cylinders, we want to store them on a flat surface so that we're not having to cut all the cylinders that come in so we can get a flat surface. If we're cutting every cylinder, that takes a lot longer than just taking the concrete out and putting it into the compressor machine. So try and store them on a flat surface so we get a flat top on them. And then we want to keep it from freezing or getting too hot. So we want to store those between 60 to 80 degrees. Obviously if it freezes, we're going to have some low strength, but also in the summer, the first day that hits 80 degrees, I was talking to 40, we're like, it's 80 degrees, in about a month, we're gonna start getting some low strength emails, hey, what do we do? We got low strengths here. And it's because, and this would be on my curb and gutter or approach valve, something like that, the cylinders were allowed to be out in the sun over 80 degrees, since we get deficient strengths in that means. We don't want to take the lids off of the cylinder molds. The lab will do that. So once you put that lid on, just do the initial and intermediate curing. If it gets to the lab, they'll handle it from there. Transporting the cylinders, the engineer will transport the cylinders from the initial curing site in accordance with the following. We're going to transport all grades of concrete except mass concrete a minimum of 16 hours after casting. Transport mass concrete a minimum of at least 24 hours after casting. If you think about it, we're trying to control the temperatures of that concrete in mass concrete, so it's taking longer to gain strength. And so we want to give it a little bit longer before we move them around. But the opposite is true if we got high early concrete. Obviously we're getting strength faster than we would on a normal concrete, so we can move those a little bit earlier if we need. Field control cylinders, so MnDOT uses these to determine or control the progress of work. So this is things like opening of traffic, stripping forms, setting beams, things like that. We recently renamed it closer to the ASTM C31 field cure. We're going to cure these cylinders in the same location and under the same conditions as the concrete structure or unit involved, because we're trying to mimic what's happening with the actual concrete in question that we want to know about. So we want to try and cure it as close to those conditions as possible. There are other things like match curing and concrete maturity that are a little bit better at mimicking those conditions than just putting a cylinder next to your pour. And so what match curing is you basically have a cooler that's got a computer that's linked to a sensor in the element that we're thinking of for temperature, and it's keeping that water that the cylinder is in at the same temperature of the element that we're wondering the strengths about. So if we're using this, we want to maintain those cylinders at a temperature no greater than 5 degrees above the temperature of the concrete out in the field, and then if the temperature exceeds that 5 degrees or the temperature monitoring system fails, that's a part of these match cure systems, then we're not going to accept those field control cylinder results because they're not valid anymore, right? Especially if it gets above 5 degrees, because if they get more heat, they're going to have higher strength than what's out in the field. Maturity, now this takes advantage of a property of concrete where every single concrete mix design, I like to call it, has like a thumbprint. And so every distinct combination that you can use for concrete, they have it's called a time temperature, or TTF. Basically, if you know the time and you're tracking the temperature, you can correlate that to strength. And so maturity is allowed. It's not used as often as I would hope it is, but again, this is a contractor preference, whether they want how they want to do control cylinders. So they could either do the control cylinders or they could use things like maturity or match curing. But I think maturity is great because once you have that maturity curve set up, all you gotta do is put that sensor in and you basically get real-time strength information on that concrete. As long as you are monitoring the temperature over time and your mix doesn't change, you can get very accurate, real-time strength information on that concrete. If you are using maturity, then we've got to develop that maturity curve. So this is in the lab. They cast enough cylinders to get strength over time, and they're also logging temperature at that. That develops your maturity curve. Then when we're estimating in-place strength, we take that maturity curve, we plot the data from our sensors in the field that are taking time, or temperature over time, and that gives us our estimated in-place strength, which is very accurate. And then we also have to validate that maturity curve relationship. If you have any questions or want to do more reading on maturity, we have a webpage dedicated to it, so you feel free to go read that, or you can always reach out to me too, because I can.
So what are the costs on that for the contractor for maturity?
You know, the initial cost is what's a lot higher because you've got to get the lab to develop it.
How about the sensors then?
The sensors, so this one here, this one probably, I don't know, a couple bucks for this one. But they also have, there's also maturity sensors out there that are embedded in the concrete that work through Bluetooth. So those are a little bit more expensive. You know, so again, there's not any like APL for maturity sensors that we have. So that's kind of at the contractor option. But they just need to be able to measure the time accurately. Now, the advantage that you would get if you use like that Bluetooth sensor is you can just walk by where that sensor location is and it's gonna upload to your phone to the cloud right away. Whereas if you're using these kind of dumber sensors, they've got wires hanging out of the concrete that you have to put a data logger, link it onto, download the data, take that data to your computer. So there's advantages, disadvantages. I think the real advantage of maturity when it comes to field control is you don't have to handle cylinders. There's a lot of things that can happen with handling cylinders where you might get a result that you don't trust, that you're not going to use that result for, or you've got to wait for the lab to break that cylinder. Whereas maturity, you can really just read your output, in real time what you're saying.
And you're only using one cylinder where normally you use to add with 3 so you can press control.
Right, exactly. Yep.
There's only one.
All right, let's talk about concrete field issues. So scaling, this is a big one. So we always hear, well, it's the salts that cause scaling. More often than not, when we see scaling out on MnDOT projects, we take a core and we put it under the microscope. It's either over-finishing, like improper finishing, or curing that is what's caused the scaling to occur. Now, de-icing chemicals, they're not the root cause of scaling, but they exacerbate it. And so what de-icing chemicals do is a couple things. One, they allow more solution to absorb into concrete. So we've got our saturation state of our concrete goes up. But then they also reduce the temperature, so we get more freeze-thaw cycles. So it's kind of a double-edged sword here. But if we place the concrete, we've got a good mix design, we place it and finish it properly, we can mitigate the effects of scaling that we see out here. And so if you're ever on a project where you have scaling, I want you to let me know about it, because scaling can be an indicator of poor air quality. And if we've got bad air on the bridge deck, we need to know about it. 999 times out of 1,000, probably more than that, it's not going to be an issue, but we need to be able to rule it out that it's not true. Gutter placement, when we're placing concrete here, obviously the bid will kick in all the way to the gutter. So we're gonna, we've got to do some hand work in order to consolidate that concrete. But also we don't want to, just because we can reach there, we don't want to just spend all day, hitting that concrete with our trowels. So it's kind of a double-edged sword. We need to be able to consolidate that concrete there. We also don't want to overwork it just because we can reach it. And like Paul mentioned, we've got some of that deck cracking issues, whether it's under deck or some of the other cracking issues that we see that we're trying to mitigate with maybe better detailing on our rebar or using different materials, fibers, but also if we're curing and placing the concrete right, then we can mitigate some of these cracking issues that we see. Now, our low slump overlays, this is what they can tend to look like. And one of the reasons why, at least in my opinion, is that this is a mix design that has 836 pounds of cement in it and hasn't changed since the 70s. But the cement grind has gotten finer over that few decades. And the finer the grind is, the faster the concrete's going to gain strength. And so, over 30 or 40 years here, with that concrete not changing, but the grind changing, we're getting faster setting concrete, shrinkage is happening quicker. So because of this, we are currently in a project to update this mix design. We've done it on a few projects and seen really good performance out of it. So I imagine in the next few years, this will we'll be updating that mix design into the standard spec for our most of
Yeah. Would I get rid of D7 using silicon fume then?
It's up to D7. Hopefully, I mean, I would like that. They did one on down in Mankato on the 14 bridge. It was one of our trials that went pretty well. So that actually was D6, but they're close enough. So no, that was D7. That was D7.
We
So
had two this year that were on TH4 South.
you did silicon fume? Yeah.
Not a fan.
Like I said, it's really, it can make really, really, really good concrete. It's just really sensitive to the moisture conditions you're placing it in. Back to low slump overlays. So we got pre-running requirements within 12 hours. Place of the concrete wearing course, we're going to put potable water to pre-rut the deck surface to do a SSD condition. Then we're going to maintain that SSD for at least 6 hours. Not allow free water on the surface, replacing the bonding agent that you put down. And then type 3 cement is not allowed, but they'd have to go out of their way to get type 3 cement, so you're probably going to have to run into that. Now let's talk about mass concrete. Mass concrete is defined as any element with the least dimension of over 4 feet. Excuse me. And that means when we have mass concrete, we don't want that concrete to get above 160 degrees. And we also have a graduated maximum temperature differential on an upcoming table that I'll show you. All of these are contractor mix designs. And part of this is, part of the mass concrete spec is doing thermal modeling. So we'll come up with a mass concrete placement plan that will have a thermal model attached to it. That's going to show things like the anticipated temperature of the concrete and then any cooling and heating and temperature control measures that the contractor can take depending on what happens during the pour. And so this is the old table in 2401 MC1. So this is a special provision always for mass concrete where we laid out what's the different elements and then what are the temperature control requirements. This caused a lot of issues out in the field because it was, well, maybe it isn't type of thing. And so what we've recently done is we've changed to this, and then the designer's responsibility to call out on the plan what is mass concrete and what is not mass concrete. And so you will see on bridge plans, and I'm not sure if they're on the plans for the class, but like if your pier cap has a least dimension greater than 4 feet, then you'll see an MC next to it. And a lot of times in abutment stems, you'll see it coming up or something like that. And so that's trying to take out some of the ambiguity in the plan and say, no, this is mass concrete. But what are we worried about with mass concrete? So there's two things. We've got delayed heterogeneous formation, or DEF, and then also thermal differential cracking. And so for that bottom one, for thermal differential cracking, let's just take this for example. We're placing this concrete, and in the middle, that's the middle of that concrete is where our highest concentration of temperature is going to be. That's about the hottest part of the concrete is going to be at the middle of that concrete. And then when you get closer to the surface, it's going to be cooler, right? It's just thermodynamics, right? You've got all that heat's getting concentrated in the middle, it's dissipating out of the surface. If that differential between the surface of that concrete and the middle of the concrete is large enough, you can start getting cracking that shows up. And so that's why we've got the differential requirements in the spec, because we want that temperature to be as close as possible so we can avoid some of this thermal cracking that can happen. When it comes to delayed heterogeneous formation, at about 160 degrees when the hydration reaction is happening, Well, let's just back up a second. Exogenite is a normal byproduct of the hydration reaction. It's one of the compounds, one of the minerals that that forms during the hydration reaction. At about 160 degrees, it stops forming. Everything else keeps hydrating, keeps going, filling up all the spaces. But then, once that concrete cools down and is in service, the exogenite will start forming again. And when it starts forming, it starts trying to find areas to form into. It starts pushing everything out, right? It starts trying to make some space for itself, and that's when you start getting cracking that can happen. And so that's why we have a max temperature for mass concrete too, is if our concrete gets above 160 degrees, then the exogenite's gonna stop forming, but it will form later. And you don't know when it will. It's really hard to forecast when that exogenite will start forming. So the best way to do it is just allow it to form during the hydration reaction anyway. So that's why we have a max peak for mass concrete. And as you can see, so we've got with our differentials, you know, the younger the concrete is, the tighter the differential is. So the concrete's a little bit older, then the differential between the center in the middle and the surface of the concrete can be a little bit wider. And this is what you might see out of a thermal control plan, a TCP. So you've got the concrete temperature or the strength or temperature, and then the differential. This is like the specified differentials, and then this is what they're modeling for the differentials to actually be. And then this is just this wavy line that's morning or that's midday and midnight. So your temperature swing throughout the day what they're anticipating. So this is a computer-generated estimate of heat generated within a mass element for our thermal control plans, and it's unique for every element and every mix. So even though your mix might not change between elements on a project, the element dimensions will, and that will change what your thermal control plan says. So we need a different thermal control plan for every different mix and different element that we're placing in. We want preliminary placement and temperature plans required at least 30 days prior to casting the element. And then we want a final placement and temperature plan within 48 hours of placement. Now, this is to update that thermal control plan with a more accurate forecast of what the temperatures are going to be. Because 30 days out, you're only kind of guessing what your temperature is going to be. You're making a big assumption. 2 days closer to the 4, you have a pretty good idea what your temperature is going to be. And so we just want to check in on that with the thermal control plans. They're going to look at the heat rise of the mix, the max temperature, and the temperature differential. The plan should tell what to do if the temperatures are exceeding the model, and then also include what are you going to do to control the temperatures, whether it's blanketing, plastic, number of layers, things like that.
So, Jake, one question on that last slide. Somebody asked last week what to do if that max center temperature is going above the maximum. So what would the plan typically be?
Plan?
What would the plan be if your max temperature is getting above? I mean, what do you do?
Well, at that point, if you place the concrete and you've got the max temperature is exceeding that, unless you have cooling tubes in that element, so the cooling tubes be able to pump water through, you're pretty much at the whim of the concrete. And we've got a table in the spec that lays out monetary deductions based on that max peak temperature. And it gets pretty, I mean, it's pretty quickly it gets to remove and replace. I think it's like $1 or $2 for 160 to 165, $1 or $2 per yard, and I think it bumps up to like 20, then 50, then remove and replace. I don't know if I have it in here or not, but it's in your spec. There's a table that says that. For the most part, most of the mass concrete that we're pouring, we're probably not going to get close to that 160. Maybe you get to 155 on the thermal control plan. If it's like a super massive element, like the St. Croix crossing, those cross beams, I think the minimum dimension was 18 feet, 13 or 18 feet or something like that, and that was 8,000 PSI concrete, so it's going to be really hot anyway. That might be a situation where cooling tubes are deployed, even though they weren't on that one, but that might be a situation where cooling tubes are deployed so that you can try and pump some water through to take heat out of that concrete. One thing I do want to mention though on these thermal control plans is the engineer does not actually approve these. We just want to be made aware of them because it's still the contractor's responsibility to place this concrete within spec. Now, so the thermal control plan, the engineer does not approve it. We're just trying to be made aware of it, of what the plan is for thermal control. Now, when it comes to when you can remove the forms for mass concrete, it's quite a bit more involved than just normally moving the forms for other elements. But all 6 of these that are laid out here need to be met before you can start moving forms. The one caveat that I want to make here is that this has come up before, that there is a difference, at least in my opinion, and maybe we need to clarify this in the spec, of what the difference is between removing forms and cracking forms is. So for cracking forms, what we're really trying to do is vent some of that interior air in that form work out, but you're able to reattach the forms readily. If you're removing the forms, basically what you're saying is I'm done with the forms on this element and I'm moving them somewhere else. So there is a difference between cracking forms and removing forms. Then let's quick talk about self-consolidating concrete. So when you have self-consolidating concrete, when you do the flow test, you take your slump cone, you flip it upside down, fill up the concrete, and you pull it up like you normally would in 3 to 7 seconds, and then you get a pancake like this. And so we want it to be flat and level, right? Because we're flowing concrete, invert the cone, and then we're raising that cone, right? Then once it's done spreading out, we're going to take two diameters and then the average of them. That's our spread. So when you do an SEC concrete, you see a spread range. The range is generally 4 inches, so it would be like 20 to 24. So when you measure the spread, you're taking the average of 2 diameters and making sure that it falls within that spread range that's on that mix design. You're also going to do what's called a visual stability index rating. Now this is a pretty subjective test, but it's a 3. There's 3 ratings you can give to it. 0 being the best, 3 being the worst. And what you're looking for is the coarse aggregates. Are they evenly dispersed throughout that pancake? And then also the edges. Do we have any kind of paste that's leaking out, kind of bleeding out of the edges? So if we don't have any of that, we've got the aggregates completely dispersed, evenly dispersed throughout that pancake, we're going to call that a 0. But then if you look at 3 here, we've got aggregate that if you were to tip this up and look at it from the side view here, you might see like a little mound of that coarse aggregate. That's obviously not spreading out with everything, so that would be a 3. And we also got a little bit more of that bleed that's coming out of the edge of the pancake there. I think our spec used to be 1 or less, and I think it's 2 or less now for our SEC when we're doing a visual stability index rating. But if you have a good SEC mix, it works really well. This was a trial pour for the Hastings Bridge. They put up some formwork. They had rebar and a corner to go through. They placed the concrete on one side of the form and it filled up the rest of it. And then afterwards, once the concrete was hardened, they cut a core out of it. And you can see you've got good dispersion of the coarse aggregate throughout that, even around the rebar there. So SEC, when designed properly and placed properly, is definitely a tool to use in the toolbox here. Schedule materials control. This one, again, I kind of do this partly because it kind of illustrates the need to make sure you're checking on your plan what schedule materials control is for your plan, because it can change depending on when that plan is signed and left. But the ones to be aware of for concrete on bridge concrete is the bridge concrete grades B, S, X, Y, HPC, and SCC. Now this has been updated a little bit, but I do want to point out, see it's not in here yet. This is an older version that when we're making our compressive strength cylinders for bridge concrete, if it's HPC, mass, SCC, then we're making another set for 56-day breaks if we need it. And that's in the current scheduled materials control. So I'm Jacob Gave, Maria Maston's a concrete engineer, and then Gordy Bruni's also he's a concrete guru as well. Maybe you've run into him or not, but great guy. If we ever have any field issues with concrete, he's gonna be involved in them. So that's contacts in the concrete office for you. Feel free to give me a shout or shoot me an email anytime you want, if you want to talk concrete.
Thanks, Jake. Any questions for Jake?
Are you finding that the fibers are changing their air content when you're testing?
Not really. No. Are you seeing that?
Yes.
Where?
You're raising them.
That's interesting. Can you do me an email on that? Let me know where you're seeing out there.
What we're learning on it is that we let the truck sit for about 2 to 3 minutes after it's mixed.
Well, I want to know
It's in
things
trapped
like.
air. It's in trapped air is what it is.
So, what part of the state is it?
Essentially.
And do you know what fibers they're using?
I have.
Yeah, let me know, because I'd like to see that. Because if it's in trapped air and you're doing the air test, if you're consolidating the concrete, right, then it should be taking out all those bigger bubbles. So,
It's raising it up probably about 1 to 2%.
that's interesting. So I guess the answer is I haven't seen that. It's first I've heard of that, so. All right, thanks, everyone. Skull bikes, huh?
Let's take 5 minutes, so like 4 minutes too, and then we'll end with a video and a menti.
Go slower.
Right on. Right on. All right. Actually, I almost I was trying to make sure that
You gonna be at the tech conference?
I think so.
Oh, good, we'll see you there then.
Yeah, there we go.
I'll be there.